Welcome back to linear algebra. In this video, we're going to be talking about Gaussian elimination. Gaussian elimination is named after the physicist and mathematician Carl Friedrich Gauss, who you may have run across in a previous course somewhere along the line. If you've ever done a study of statistics, Carl Friedrich Gauss did a lot of work with the normal distribution. And the equation for the normal distribution, the equation that produces that curve, is called the Gaussian formula, and the bell curve is sometimes called the Gaussian curve in his honor. If you've ever done a study of electricity and magnitude, Gauss's law is one of the four major ideas of electricity and magnitude. It's one of the four pieces of Maxwell's field equations, which defines electricity and magnitude. The Gauss is also a unit of magnetic intensity, so very certainly prevalent in that field as well. The process of Gaussian elimination is a way of codifying and simplifying the tools that we talked about previously for solving a system of equations. Almost certainly none of these tools were actually invented by Gauss. We have evidence that they were well established for hundreds of years, if not thousands of years prior to Gauss's work. But Gauss popularized them. He wrote them down, he formalized it as a series of steps, and for that reason, they are named after his honor. All right, let me get my head out of the way and let's get into this. Gaussian elimination is a process of solving a system of equations. So the first thing we're going to need is a system of equations. Whoops. There we go. That's all we need. This system of equations should be familiar to you. It's the same system of equations that we studied in the previous video. And so we're going to try to work with this. And one of the first things I want to do is streamline our presentation. If you look at the system of equations, or if you look at any system of equations, it's not a very efficient way of writing down the information that's necessary. In every equation in a system of equations, you have some number being multiplied by x1, you add or subtract, you have some number, you multiply by x2, you add or subtract, you have some number, you multiply by x3, you keep going. If there's more variables, you write down an equal sign, you write down a constant. When you're first learning differential equations, having all of these pieces is certainly useful. But now that you are very comfortable with systems of equations, having all that extra stuff is kind of just baggage. And so we get rid of it. We're going to create what's known as an augmented matrix. If you've not worked with a matrix in the past, two things you should know. First of all, we're going to spend several weeks talking about the properties of matrices later on in the course. So if you're not familiar with all of those, they'll come up as we need them. But for right now, a matrix is a two-dimensional array of numbers. You can think about a vector as a one-dimensional array of numbers. We talked about both row vectors and column vectors previously. If we have a construction which has numbers in both rows and columns, we call that a matrix. And we're going to make this matrix, we call it the augmented matrix, by looking at the coefficients and the constant term in each of the equations in this system. So the coefficient on x1 is 1, we write down a 1. The coefficient on x2 is -1, we write down a -1. Another -1 on x3, and then my constant is 2. We just take those things and we copy them over, and doing that allows us to suppress a lot of notation. We still need a minus if there's subtraction, but we don't need a plus when there's addition. It's implied. We don't need to write down the names of the variables. We know that they're going to be x1, x2, x3, and so on. We don't need to write down the equal sign. It's just there. When we look at this matrix, we often split it into two parts. You can see here that I have this vertical line drawn. You don't always see that. In several sources I've come across, they'd write out the augmented matrix like this without a vertical line present at all. Um, that's not the button I wanted. I'm really having trouble with technology today. I apologize. Right. I'm going to leave the vertical line in. I find that it makes it a little bit easier when you're first learning the ideas of Gaussian elimination. Having it there helps you separate in your brain the coefficient matrix, the part of the augmented matrix that came from the coefficients on all the variables, and the constant vector, the part of the matrix that came from the constants on the right-hand side. Right? I do call this a constant vector, not a constant submatrix or constant matrix, because it is just one column. And when you have just one column, it's a vector. If you have multiple rows and multiple columns, that's when you have a matrix. There will be times when treating all vectors as matrices is useful, but by and large, being able to think about the special properties that come of vectors when you have just the one row or just the one column is going to be more to our advantage. Right. Once we have an augmented matrix to work with, instead of thinking about operations on equations in a system, we're going to rephrase this as elementary row operations. The first one, interchange two rows, is not something you think about all that much when you're thinking about solving a system of equations. But if we took two of the equations and wrote them in a different order, it wouldn't change the system at all. We would have an equivalent system. So that's certainly something that we can agree is perfectly valid as something to do to a system of equations. So it's perfectly valid as something to do to an augmented matrix. Right? The second elementary row operation is to multiply a row by a non-zero constant. Multiplying a row in a matrix by a non-zero constant is the same thing as multiplying both sides of an equation by that constant. If the constant is zero, you lose information, but for any other constant, that works perfectly fine. Right? If you get your equation down to just one variable and you have something like 5x3 equals 10, you want to divide both sides of the equation by 5, or equivalently, multiply both sides of the equation by 1/5. That's the process that this operation, this elementary row operation, is trying to get us to do. The third thing we can do, the third elementary row operation, is add a multiple of one row to another row. And again, that's something that we did when we solved our systems. We would take one equation. Sometimes you would multiply both equations by something, which we can simulate by doing steps 2 and 3 or operations 2 and 3 in sequence rather than trying to rely on just one. But we would take an equation, we would take the other equation, we'd multiply it by something, we'd add them together, and we'd get a new equation. That is absolutely something we do solving a system of equations. And so it should be perfectly reasonable as an elementary row operation. The terminology in linear algebra gets to be quite a mouthful. So you will frequently see the idea of an elementary row operation abbreviated as ERO. Um, Most things in linear algebra get abbreviated because, trying to say them is just too much. But let me go ahead and copy this matrix that we've already worked with. We know what the solution is going to be. And let's bring it down here and look at doing some elementary row operations. Thinking back, if you remember what I did when I was solving the system of equations, I multiplied the first equation by 3 and subtracted it from the second. I multiplied the first equation by 2 and I subtracted it from the third. The notation for describing what we're going to do with that is like this. We're going to draw an arrow, and I'm going to use a cute pun. Using the Greek letter rho. So I'm going to take row 2. Yes, I'm going there. The second row is the Greek letter rho subscript 2. I'm going to take row 2 and I'm going to subtract 3 times row 1 from it. So the first row is going to stay the same. The second row is going to be the operation. So I have 3 minus 3 times 1, which is 0. I have negative 3 minus 3 times negative 1, which is 0. I have 2 minus 3 times negative 1, which is 5. And I have 16 minus 3 times 2, which is 16 minus 6, or 10. Then my third row is going to stay the same. Now continuing the pattern, I'm going to take my third row, row 3, minus 2 times row 1. So my first row stays the same. My second row stays the same. And then my third row, I do the subtraction. So I have 2 minus 2 times 1, which is 0. I have negative 1 minus 2 times negative 1, which is positive 1. I have 1 minus 2 times negative 1, which is 3. And I have 9 minus 2 times 2, 9 minus 4, which is 5. Up next, I'm going to swap the second and the third rows. I'll denote that using something like this. Row 2, double-headed arrow, row 3. I'm swapping row 2 and row 3. So the first row stays the same. The second row is now the third row. And the third row is the old second row. One last operation. I'm going to multiply the third row by 1/5. Again, that's swapping two rows doesn't really seem like it does anything, but it makes our lives a little bit easier. Multiplying by 1/5 is dividing by 5. That third row, if you turn it back into an equation, says 5x3 equals 10. You get x3 by itself by dividing both sides of the equation by 5. And depending on which theory you subscribe to, this might be your stopping point. This matrix is now in what's known as row echelon form. There are a couple of specific properties that you're looking at in row echelon form, but the way I like to think about it is very visual. I want to be able to draw a triangle so that that triangle has all zeros in it. Being able to draw that triangle at the bottom left of the augmented matrix where everything is a zero is the way of recognizing that you have row echelon form. Right. Specifically, any row which contains only zeros has made its way to the bottom of the matrix. We don't have any rows containing only zeros in this particular matrix, but if we did, they'd have to be at the bottom. Any row with non-zero entries has a leading entry of 1. Right. A leading entry is the first non-zero entry reading from left to right in a row. All right, so the first non-zero entry in each row is a 1. First entry in this row is a 1. We've got a 0. The first non-zero entry is this one. It's a 1. We've got a 0. We've got another 0. The first non-zero entry in this one is also a 1. The other thing that we want for row echelon form is that every entry below a leading entry is 0. We've got a leading entry here. The rest of the column is 0. We've got a leading entry here. There's a non-zero entry above it, but everything below it is a 0. We've got a leading entry here. There's nothing below it at all. All right. Those properties are the properties that give you row echelon form. And again, there's some debate as to how to set this up. Actually, some sources don't require the lead entry to be 1 for row echelon form. They just require you to label that leading entry and think about the zeros being below it. And We could stop there. At this point, we can turn this into a system of equations. That third equation tells us that x3 is equal to 2. We can plug that value into this equation and figure out what x2 is. We can plug those values into this equation and figure out what x1 is. We are at the point where back substitution is really easy. But we could also keep going. Row echelon form is great, but even better would be to get to what's called reduced row echelon form. And in reduced row echelon form, we're going to just take this one step further. Not only do we want every entry below the leading entry to be 0, we're also going to require that every entry above the leading entry is also 0. So just keep going with this. Actually, I'm running low on room, but let's see if we can get this to work out. I'll start with this one. It's the simplest row. It's got a leading entry of 1, and we've got some non-zero entries above it. So if I take row 1 and add row 3 to it, then the 1 and the -1 will cancel out, and I'll have a 0 there. And we've got the basic idea of row operations. I feel comfortable doing more than one row operation at a time. If I take row 2 and I subtract 3 times row 3, I'll get a 0 in the third column of that row as well. All right, so 1 minus 0, or I'm sorry, 1 plus 0 is 1. -1 plus 0 is -1. -1 plus 1 is 0. And 2 plus 2 is 4. 0 minus 3 times 0 is 0. 1 minus 3 times 0 is 1. And 3 minus 3 times 1 is 0. 5 minus 3 times 2 is 5 minus 6, which is -1. And then the third row, 0, 0, 1, 2, stays the same. We're almost there. We've got one step left to do. All right, here's my leading entry, zeros everywhere else. Here's my leading entry, zeros everywhere else. This leading entry has a -1 above it that we need to fix. We can fix this pretty quickly by just taking row 1 and adding row 2. So 1 plus 0 is 1. -1 plus 1 is 0. 0 plus 0 is 0. 4 plus -1 is 3. The other two rows stay the same. Reduced row echelon form asks us to keep going until we get to the point that each leading entry is the only non-zero entry in the column. And reduced row echelon form is amazing when it comes to trying to solve a system of equations. Because now that we have done this, look at what happens when we back substitute, or when we translate this back from a matrix to a system of equations. We get 1 times x1 plus 0 times x2 plus 0 times x3 is equal to 3. We get 0 times x1 plus 1 times x2 plus 0 times x3 is equal to -1. We get 0 times x1 plus 0 times x2 plus 1 times x3 equals 2. And in fact, the right-hand column where the constant vector was originally, when we get to reduced row echelon form, if there is a unique solution to the system, that column will give us the solution vector. All right. The process of working through and finding reduced row echelon form, well, finding row echelon form using matrix operations, using elementary row operations, is Gaussian elimination. And it's really just solving a system of equations in a compact form. Continuing onward until you get to reduced row echelon form is a modification by another mathematician, so it bears the combined name Gauss-Jordan elimination. That's going to be most often what we're looking at. If you can get to row echelon form and it's relatively simple, sometimes writing it as a system of equations and back substituting is faster. But generally speaking, getting all the way to reduced row echelon form is the more efficient way of solving the system. Let's take a look at one more example here. Here I have, that's a terrible brace. Here I have a system of three equations in four variables. X1 minus x2 minus x3 plus 2x4 equals 1. 2x1 minus 2x2 minus x3 plus 3x4 equals 3, minus x1 plus x2 minus x3 equals -3. And we could solve this system using operations on the equations and go through the algebra that way. But I hope that even in that just one example has convinced you that if we take the time to write out an augmented matrix, it's going to make the process much more efficient. Not necessarily easier, but more efficient. It's less writing, it's more streamlined. And we can just start into it and see what we get. All right, I notice immediately my first row, my first column is a 1. Right? My goal in Gauss-Jordan elimination is to get the first row, first column to be a 1. The next step in Gauss-Jordan elimination is to take out the rest of the column. Figure out what you need to do in order to make the other entries in the first column 0. In this case, if I take the second row, which has a 2 in it, and I subtract 2 times the 1 in row 1, then it will be 0. And if I take the third row, which has -1, and I add the first row, which has +1, it will be 0. All right, so my first row stays the same. 1, -1. Space this out a little bit more nicely. 1, -1, -1, 2, 1. My second row, I'm taking row 2 minus twice row 1. So 2 minus 2 times 1 is 0. Negative 2 minus 2 times negative 1 is 0. Negative 1 minus 2 times negative 1 is negative 1 plus 2, which is positive 1. Then I've got 3 minus 4, which is negative 1. And I've got 3 minus 2, which is positive 1. The third row is a little bit simpler calculation-wise. Negative 1 plus 1 is 0. 1 plus negative 1 is 0. Negative 1 plus negative 1 is negative 2. 0 plus 2 is 2. Negative 3 plus 1 is negative 2. All right, so first row, first column, I've got a 1. I've got everything else 0. I'm good. In the second row, my lead entry is in the third column. In my third row, my lead entry is also in the third column. There is no lead entry in the second column. That is something to take note of. Because there is no lead entry in the second column, we don't really have to do anything with that. So in the third column, we want our entry third column, second row to be a 1. So we have our lead entry of 1. And hey, we've got that going on right now. So we don't have to do anything to get that entry to be 1, which really makes our lives easier. Now it's just a matter of getting the rest of that third column to be 0. And we can do that using a couple of elementary row operations. All right, we've got a negative 1 in the first row. So we want to add 1 to it, which is really just the entry in the second row. So row 1 plus row 2. The third row has a negative 2. We want to add 2, which is twice what's in the second row. So we'll take row 3 plus 2 times row 2, and that will give us that entry. All right, so term by term. First row plus second row. 1 plus 0 is 1. Negative 1 plus 0 is negative 1. Negative 1 plus 1 is 0. 2 plus negative 1 is 1. And 1 plus 1 is 2. Second row stays the same. 0, 0, 1, negative 1, 1. Third row plus 2 times the second row. 0 plus 2 times 0 is 0. 0 plus 2 times 0 is still 0. Negative 2 plus 2 times 1 is negative 2 plus 2, which is 0. 2 plus 2 times negative 1 is 2 minus 2, which is 0. And negative 2 plus 2 times 1 is negative 2 plus 2, which is 0. Right. Notice in this case, the last row of my augmented matrix is a row entirely of zeros. We do need to make sure that that happens. Well, when that happens, that row is at the bottom of the matrix. It is in this case, so we're in great shape. We've got a leading entry in the first row, which is a 1. We've got zeros everywhere else in that column. We've got a leading entry in the second row, which is 1. We've got zeros everywhere else in that column. We've got a couple of variables where it didn't quite work out like that, and that's okay. But we have gotten this matrix into reduced row echelon form, and that's what we wanted to do. Now that we have that, we can go back, we can rewrite this as a system of equations. So we've got x1 minus 1 times x2, 0 times x3, 1 times x4, equals 2. we've got 0x1, 0x2, 1x3, minus 1 times x4 equals 1, and that's it. Those are the two equations in our system simplified. The first row, first column, and the second row, third column were our lead entries. Those correspond to the x1 term here and the x3 term here. Whenever you are working with a system of equations and you get the equation in reduced row echelon form, or get the matrix in reduced row echelon form and turn it back into equations, the lead entries are going to correspond to a variable that appears exactly once in the entire system. That's worth noting. We'll call those the lead variables. Lead variables correspond to the lead entries of the matrix. The variables that are left, in this case x2 and x4, are known as free variables. And we can always take our system of equations, solve for the lead variable in terms of the free variables. It is always something we can do. In this case, that gives us that x1 is x2 minus x4 plus 2, and that x3 is x4 plus 1. Then we take each of our free variables and we assign it a parameter. Starting with s and t is a common choice. You don't have to do that, but it seems to be the norm. So we'll write that x1, x2, x3, and x4 well, x2 is a free variable. Let's just call it s. x4 is another free variable. Let's just call it t. x1 had x2, which is now s, minus t plus 2. And x3 had x4, which is now t plus 1. All right, and there is our solution. Pick any real number s, pick any real number t, plug those things in, and we have our solution. So we could write the solution set as the set of all s minus t plus 2, s, t plus 1, t, such that s and t are real numbers. That's perfectly valid. That is absolutely the solution set. I can clean this up a little bit and get these brackets all of equal size, because as bad as my writing is, doing things like that makes it a little bit easier for me to understand what is happening when I try to look back at it later. But if we want to clean up a little bit further, we can. We'll explore why this can be useful in a later video. But something that you might notice that we can do with this vector is split it up. The first two components of the vector have an s in them. The other ones don't. 3 of the vectors, but not all 4, have a t in them. And the first and third coordinates of the vector have constants. Then I can factor out my parameters. and write the vectors in my solution set as a linear combination of vectors like this. We will explore in the upcoming videos why this can be useful. But for right now, I just want you to see that it is a thing we can do. We could, if I scroll up just a little bit, we could write our vectors, our solution as a single combined vector. That is perfectly valid. It absolutely works. Or we can split the vector up and we can realize that our solution is actually a linear combination of three vectors. It's not any arbitrary linear combination because this last vector has a fixed coefficient of 1, but we have two vectors here which each have an arbitrary coefficient. This is a linear combination of two vectors. All right. Why that is useful, again, is something we're going to be exploring a little bit later on. For right now, I just want you to see that it is, in fact, something that works. Before I wrap up on this topic, a little bit of theory that the new approach opens up for us. The rank of a matrix is the number of non-zero rows which appear in the row echelon form, which I'm abbreviating as REF, of the matrix. And with that little bit of vocabulary, I can write out a relatively easy to understand theorem. For a system of n variables with coefficient matrix A, the number of free variables in the system, in the solution, is n minus the rank of A. And the proof of this theorem is a lot more straightforward than you might think. Although it's a challenging theorem because it involves no algebra whatsoever. Every variable is either a leading variable or a free variable. That's kind of the definition. The free variables are every variable which is not a leading variable. My next claim feels like it's being overstated, but we really do need that much detail. The definition of a leading variable is the variable that corresponds to the leading entry or to a leading entry in the matrix. And when the matrix is in reduced row echelon form or even just row echelon form, each row has one leading entry. It's the first non-zero entry. Any row that is all zeros does not have a non-zero entry and so does not have a leading entry. So every non-zero row has a leading entry. Every leading entry is a leading variable. Every leading variable comes from a leading entry, which is coming from a non-zero row. Or to put that more simply, the number of non-zero rows in the matrix in row echelon form is the same as the number of leading variables. And of course, the number of non-zero rows is the rank. So putting all of that together, if you're dealing with a system that has n variables, and we know that the number of leading variables is rank of A, and we know that every variable that is not a leading variable is a free variable, then just count up how many are left. Take the n variables, subtract off the leading variables, the rest of it is the free variables. I love proofs like this because it's entirely a logic proof. If you think about what the words mean, it makes perfect sense. It is very understandable. But if you don't think about what the words mean and you try to approach it from an algebraic perspective, there's not enough information. Right? I'm very unlikely to ask you to write a logical proof like this at any point in the course, but I think that understanding how the logic works and even just the fact that everything we do in math is based around logic like this is very important. There's a really nice conclusion that we can get to from this theorem. I'm going to call it a corollary. A corollary is a result that follows very naturally from a theorem and doesn't take that much more thought to try to write out. A homogeneous system of m equations in n variables will have non-trivial solutions if m is less than n. Right? That doesn't seem to be related at all to the theorem that we just proved, although the relationship is very very apparent once we get into it. But more than that, I want to stress on the statement of this corollary. This is a one-directional relationship. If this inequality is true, then there are non-trivial solutions. That doesn't mean that it is necessary for m to be less than n. It is only sufficient. When we know that m is less than n, we know we have non-trivial solutions. There could be non-trivial solutions even when this is not the case. If you write the same equation 20 times and the equation only has 3 variables, well then m is not less than n. But you don't actually have 20 equations. You have one unique equation rewritten a bunch of times. So you have to be careful with the language. And that's, again, a lot of what I want to think about in this. But we do know that in a homogeneous system, if there are fewer equations than there are variables, there will be non-trivial solutions. The proof is just 2 lines. The rank of A is less than or equal to m. So the number of free variables is greater than or equal to n minus m, which is greater than 0. You may have to stop and think about each of those statements before they make sense to you. If the rank of the matrix, remember the rank of a matrix is the number of non-zero rows in row echelon form. M is the number of total rows if there are m equations in our original system. So if there are m total rows, worst case scenario is that none of the rows are all 0, in which case the rank of A is equal to m. If there are 0 rows, then the rank of A is going to be smaller than m because some of the rows get deleted from the conversation. Then the number of free variables is equal to n minus the rank. Well, if m is bigger than the rank, then the number of free variables is, if m is smaller than the rank, subtracting m instead of subtracting the rank is going to give us something that is going to underestimate the number of free variables. And since m is less than n minus m is positive. So there is some positive number of free variables. And whenever there are free variables, we have an infinite number of solutions to the system of equations. It's an interesting thing that we can get from a relatively simple looking result. We now have a condition. It's not necessary, but it is sufficient to find out when our homogeneous system has non-trivial solutions, which is one of the things that we said we wanted to do in the first place. So let me get my head out of the way. And I want you to look at exactly that. Let's take a look at another homogeneous system. X1 plus x2 plus x3 plus x4 is equal to 0. X1 plus x2 minus x3 is 0. 2x1 plus 3x2 is 0. This is a homogeneous system. It is a system of 3 equations. It has 4 unknowns. There are more unknowns than there are equations, so we know that there should be infinitely many solutions. There's going to be non-trivial solutions. I would like you to practice the process of Gauss-Jordan elimination by finding the solutions to this system. Right? Take a few minutes, see what you can do with that one. I'll see you in the next video.